In this lecture, we're going to discuss some statistics and how they relate to quantum mechanics and things like uncertainty and average values and that. Now, measurement in classical physics is very different than it is in quantum mechanics. So, when you think about classical physics, you think about a single measurement of something. You set up some experiment, you make a measurement, it actually tells you a lot about your system. So, simple example is if you imagine projectiles from your intro physics course. So you launch some projectile at a given angle, you measure that launch angle, and then you say measure the range, how far it the projectile went. If you make those two measurements accurately, you can determine a lot about the initial conditions. Specifically, you could tell me what the initial velocity was of that projectile. Quantum mechanics, it's a very different situation. A single measurement is actually pretty useless, right? So the example we've been using throughout this course so far is the Stern-Gerlach experiment. If you were to make a measurement of a spin 1/2 particle using a Stern-Gerlach analyzer and measure, say, that it was spin up, get that result, it really doesn't tell you anything about the initial state. The only thing you can really say is it wasn't in spin down, but it could have been in any general state that, any linear combination of up or down, or pretty much any state in that Hilbert space, because that measurement is probabilistic, as we saw in postulate 5. So very different things. When you look at single measurements, quantum mechanics, not very useful to us. Classical physics tells you a lot about those initial states. So what we typically do in experimental physics in that, though, is we make repeated measurements. We set up measurements, repeat them several times to kind of improve our results, so to speak. In classical, it essentially reduces uncertainties, right? You could set up that projectile, launch it a bunch of times, measure the range and initial angle every time. There's going to be some noise in that measurement, but as you can make several measurements and average that out. In quantum mechanics, you can set up your system in this, identically, so it has presumably the same initial state, and make repeated measurements of identically prepared systems. And after you do that, you can come up with sort of determining the probabilities that each measurement outcome has. So as we go through that, again, as I mentioned, classical physics, we'll typically do in experiments is we'll measure some experiments several times. Then we'll take the average result of those experiments and say that's our sort of the what we believe to be the actual value we were trying to measure. And then we'll ascribe some uncertainty to it. Typically what we'll use is the standard deviation. There are several cases where there's more appropriate metrics for that variation, but typically standard deviation works. So we'll get something like this. So if we were to make some measurement of range, let's say we set up this experiment and measured it thousands of times, and then just count, how many times did we get a result of 50 meters or 45 meters or whatever, and then create sort of a histogram. We'd have some spread in those values, and we would say, all right, from our measurement and our analysis, we're confident that this is the average value, or this is the value we measured for that thing we were measuring, and we're confident it's plus or minus, the width of this histogram. In quantum mechanics, we have an analogous sort of thing we can look at, and that's what we're going to spend the rest of today's lecture discussing. So, if we were to repeat a bunch of measurements of some system when we're looking at some physical observable, we would take, and we wanted to look at the average value of that. Well, in quantum mechanics, we would do this. Let's say this observable, we'll call it X. The notation here is it comes from probability. It's called the expectation value. But essentially, if we were to take the average of all of those measurements, well, we'd have to know what the measurement values were. So what are the eigenvalues of that observable X? We'll call them A, B, C, et cetera, and so forth. And let's say N sub A was how many times we achieved the result where our measurement result was A, and N sub B was like the same thing for B, and likewise for C. We would take all of those measurement outcomes, add them all up, then divide by the total number of measurements, and that would give us our average value of our measurement. We can rewrite this, separate all of those individual terms, and what we realize is the number of times we measured outcome A over the total number is actually, in the limit of large N, is the probability that we would measure result A, likewise probability of B. So our expectation value is essentially the sum of all the possible measurement outcomes times the probabilities of measuring that result. And that gives us what we call our expectation value. Now, for the Stern-Gerlach experiment, that would look something like this. Our expectation value for the Z spin angular momentum measurement would just be the result of measuring a spin up, h bar over 2, times the probability of achieving that result, plus negative h bar over 2, the outcome of measuring a spin down particle, times the probability of measuring that spin down particle. Postulate 4 tells us what those individual probabilities are. So we can actually, just looking at the operators and things we've discussed, determine what that expectation value should be. So when we do that, for the Stern-Gerlach case, we just plug in what those probabilities are, and it's whatever that input state was, inner product with the measurement outcome eigenstate squared times what the measurement outcome is. When we do that, it looks like this, right? We take that inner product squared with itself. We have to do the complex conjugate thing again, and we get this. These h bar over 2 and negative h bar over 2 are actually the same thing as that spin in the z direction operator acting on those kets, that spin up ket or that spin down ket. That's gives us those values, so we can make that substitution. Then we can just sort of factor out the input ket bra, the input ket size and the input bra size, and what we're left in the middle is the spin in the z direction operator times what is actually the spin up ket bra outer product, and the spin down ket bra outer product. And if you recall, the completeness relation tells us that those two outer products are an actually way of writing the identity operator. So the identity operator acting on the ket just returns that ket, so we can get rid of that operator in brackets, and we're left with the expectation value of the spin in the z direction is just that operator sandwiched between the state bra and the state ket of whatever the system we're measuring is. In terms of matrix elements, we can just represent that as, well, we have a row vector that represents that general bra, times our SC operator, times our column vector representing that state ket. And then when we carry out that operation, we end up with a squared times h bar over 2 plus b squared times negative h bar over 2. And that's what it is. The a squared is the probability of measuring that spin up state, and h bar over 2 is the result of that measurement. Likewise, b squared is the probability of measuring a spin down state, and negative h bar over 2 would be the result of that measurement. And for some general operator A, we can write it in terms of these matrix elements as just the sum of all the eigenvalues of that measurement operator times the probability that those eigenvalues are measured. So that's how we deal with expectation values. They kind of map to averages the way you might expect in classical physics. It's just we're looking at quantized states, and we're using this sort of Dirac notation and sort of some of the formalism we've developed. So let's look at some examples real quick. Let's say we have a system we've prepared in a spin up in the z direction state, and we're making a measurement with the Stern-Gerlach analyzer aligned in the z direction. Well, our expectation value for those measurements would be just this, that spin up bra and spin up ket sandwiching that spin in the z direction operator. We know that that operator acting on the spin up ket returns an eigenvalue of h bar over 2. We can bring that out. The inner product of spin up and spin up is 1, so we get the expectation value of h bar over 2, which is kind of exactly what we'd expect if we know the state is spin up and there's no contribution from the spin down ket in that general state. The probability is 100% we're going to measure it as spin up. And if we average a bunch of measurements of that h bar over 2 eigenvalue for the spin up state, we get an average value of h bar over 2. So another example we can look at is the spin up in the y direction state. Let's say we've prepared a beam in that state and we're measuring it again with the Stern-Gerlach analyzer aligned in the z direction. Well, our expectation value looks like this. It's just the bra and ket for the state of the system sandwiching that operator that kind of represents that measurement or the observable. We then want to write that bra ket sandwich in a single basis, right? We know our spin operators in the z basis, so let's just turn that bra and ket into how they're written in that z basis, which is just spin up minus I spin down for the bras and spin up plus I spin up down for the kets. We can then, you can do this a few ways. The one way is to just kind of have the same way you would do sort of algebra, first inside outside last, where we have the spin ups and spin up sandwiching the SC operator, the negative I spin up and the spin down sandwiching, and so on and so forth through this. Only two of these terms will be non-zero, right? Because that SC operator is acting on eigenvectors, so it's not going to change any of those kets. And the spin up and spin down bra and ket are orthonormal, so those middle terms are going to be zeros because the minus and the plus inner products are going to be 0. So we're left with the first term, which will give us an h bar over 2, and the last term, which will give us a minus h bar over 2. So our expectation value for measuring the spin in the z direction of a state system that's prepared in a spin up in the y direction is actually 0, which again makes sense, right? We know that a spin up in the y direction state is equally likely to be measured as spin up as it is spin down when measured in the z bases. So if we were to make thousands of measurements of this, half of them would be up, half of them would be down. We'd average them and get 0, right? One thing that's important to note, and we're going to go through this a few times today, or mention this a few times today, is that is not what you expect for any individual measurement. No measurement of the z component of the spin in a spin 1/2 system is ever going to be 0. It's either plus or minus h bar over 2. But if we measure infinite number of these, the average will be 0. All right, so now what about the spread in this data, right? In classical mechanics, we repeated a measurement a bunch of times, took an average. There would be some noise on that, and we'd have sort of a plus or minus some metric for how much the data is spread around what our average value was. What we typically use is the root mean squared deviation, which can be written this way. It's essentially the difference between the individual measurement and the average measurement squared and then all squared rooted. So just to kind of give us some visual representation of that, let's say we were measuring something, we measured it 10 times, and those dots are our values. We take the average and we get the mean. That's the expectation value for A. That's the blue line there. Now for each individual measurement, we would also take what's the difference between that individual measurement A and that average value, right? So we want to know the distance or the spread or how far that point is from what ended up being our average value. But if we were to just average that distance, take the average, well, some of these would be positive, some of these would be negative, and it turns out the way you take the mean is all of those would cancel and you would have a 0 average. So what we do is we take the square of that, so we have all positive numbers, and then square root it. So essentially we're getting the magnitude of the distance between each measurement and the average measurement value. This can be rewritten another way. You just expand that, the squaring the brackets, and it simplifies to the average value of a squared minus the average value of a squared. So there's a subtle difference there. A squared, the average value of that is not the same as the average value of a squared. So let's look at an example of this. Going back to that, we're measuring a spin up in the z direction state with the S sub z Stern-Gerlach analyzer. The expectation value for S sub z squared is just that. Take that state of the system, bra and ket, and sandwich whatever the operator is, which is SZ squared, right? That S sub z acting on spin up gives us an h bar over 2. We can then take the second S sub z, act on it again, gives us another h bar over 2. That expectation value of S sub z squared is h bar over 2 squared. So if we want to look at that RMS deviation, or sort of the spread in our measurement, it's that equation S sub z squared, the expectation of value of that, minus our expectation value of z all squared, which in this case we saw the expectation value for the S sub z measurement in a few slides ago. It ends up being h bar over 2 squared minus h bar over 2 squared, or 0, which again makes sense. If we were to make a bunch of measurements of the spin up state in the SC bases, every measurement would be h bar over 2 positive. So there's no spread in that data. We have a bunch of measurements of the exact same value. The spread is 0. What about the spin up in the y direction value we did before? Well, same thing. The S sub z squared expectation value is just sandwiched in that way. Again, convert those spin up in the y direction bra and kets into the z bases because we want to act in one state. Apply the first S sub z on those kets. They bring out an h bar over 2 and a minus h bar over 2. Do it again. We end up with the h bar over 2 squared plus I h bar over 2 squared. We can then factor out that h bar over 2 squared, and we are left again with just the inner product of what turns out to be our spin up in the y direction, bra and ket, which is equal to 1. So that S sub z squared expectation value is h bar over 2 squared. So what is the sort of spread in a measurement of that, or the root mean squared deviation? Subbing in the values that we've shown, that we've kind of walked through so far, and plugging them in to get that RMS deviation, we get h bar over 2 squared minus 0. Remember, the expectation value for an S sub z measurement of spin up in the y direction was 0. So our spread is now h bar over 2. Again, this makes sense. If I measure a spin up in the y direction state, if I make an S sub z measurement of that, half the measurements will come out as plus h bar over 2, half the measurements results would be minus h bar over 2. My average measurement is going to be 0, and that data is going to be, all those measurement results are going to be spread plus or minus h bar over 2. That's a good metric for the spread. One thing, again, that we have to stress here is we have not actually discussed experimental causes. Like, this isn't, we've sent our beam through, it gets split, but, we can only measure distances to some certain value, so there's some noise on each individual measurement. We've assumed an ideal perfect measurement system, so each individual measurement is exactly precise in this case, and we still have this fundamental limit of h bar over 2 as being a limit to our sort of uncertainty in that measurement. If we were to actually make these measurements, there would be some noise due to our limited precision of those measurements, and we would still have that added on top of this. right? So when we do that, like histograms of those measurements would be smeared values around h bar over 2 because, no measurements, there's going to be some engineering things that go in there where it's not going to be perfect. So there's going to be some uncertainty in precision of each individual measurement, but the spread is still going to be there. That is not a result of us being sloppy or not very precise in our measurement. It's a fundamental thing. We still have experimental uncertainties, because, maybe we were using an electromagnet to bend these beams and there was some, voltage or some current noise in that. So the magnetic field wasn't constant. So it was slightly different in the gradient we were using or something. We still have those added on top of this fundamental sort of uncertainty of h bar over 2. So hopefully that's clear. We're going to, as we go on in the next few lectures, we're going to start to discuss, you've probably all heard of the Heisenberg uncertainty principle and how there's limits to uncertainty. This is kind of what we're getting at, and we'll get more into this as we go.